Now we might be able to take the strings and do some analysis on them. We might be able to figure that out. But the goal is that encrypted data should appear to be as random data. That's what we want, right? In this case, the first string was echo UTOSC. I piped it to AES pipe and then converted that binary to characters. And the second string was some WRAMs. Okay. So a few points before we continue. First, as an attacker, knowing the cipher that encrypted the message doesn't necessarily give you any advantage on breaking that message. Now, granted, if it's ROT13, that might be a different story. But if it's AES, a standard that's been around since 2001, it's withstood the test of time. It's got cryptanalysis on it daily. So if you have an encrypted message with AES, that doesn't necessarily help you knowing that it's encrypted with AES. You still got a mountain load of work to do to try and break encryption. So as a result, many software utilities, like LUX or PGP, will put that sort of information in a header or in packets, right? And this can be convenient for other tools who want to utilize the crypto, okay? So for example, for LUX, if I have a USB thumb drive that is encrypted with the LUX container, it will have about a 512 kilobyte header that will have my password that I used to encrypt and decrypt. It'll be hashed, which the password will be there. The algorithms that are used to encrypt and decrypt the data on the disk will be there. And other metadata about the encryption will be in this header. This is convenient because if I plug my USB drive into my computer can scan that information and say, oh, I know this is encrypted, give me the passphrase, I'll decrypt it and mount it for you automatically. So that can be helpful. So we get a little bit of convenience having the header. A drawback of having it in the header is we lose plausible deniability. Okay? Just recently, I had the opportunity to cross the US border going through the Theater Security Administration. And they wanted me to take out my laptop. They asked me to power it on. And then they have a little wand with a little cloth traces of gunpowder as they wipe the laptop. And the guy asked while he was wiping it and booted up, and it said no operating system could be found. Now, I knew I was going to be faced with this, so just in case, I wiped the master boot record on my hard drive so it intentionally wouldn't boot. And the idea was that if they wanted to scan my hard drive and they power on the computer, I could say, wait a minute, my computer was working before you touched it, what happened? And put the pressure on them, then maybe they won't ask for the password to my encrypted partition. But he did ask, as he powered on and said, no operating system, he says, oh, do you have an encrypted hard drive? I said, no, I don't. Okay. And we went about our way. That was it. Disaster averted. But nevertheless, it happens. And if you read Bruce Schneider's blog, he covers the TSA extensively, and unfortunately, many American citizens have been subject to their hard drive being searched without warning, and they've been forced to hand over their encryption key to their hard drive. At any event, the point is, LUX announces this. So had he wanted to push the envelope, he could have seen that my hard drive is LUX encrypted, and then I no longer can deny that it's not. It's there. It's advertising that it is. So with that header, you do use that. Okay, so for this presentation then, I'm going to do cryptanalysis using bitmaps. I could spend a lot of time throwing up mathematical formulas on the board, going over number theory, going over all that stuff, but it's boring, and to be frank, I don't even understand a lot of it, and I have a degree in mathematics. So let's get something that we can see our teeth into, and that's images. So what I'm going to do is I'm going to take an image, and I'm two images, and I'm going to compose them through subtraction or through difference, and I'm going to see what the resulting image looks like. If you have image magic installed on your computer, there is a composite function that will allow you to do this, and that's what I'm taking advantage of. So I compose the difference of two images, in this case image1.bmp and image2.bmp, and the result will be called int.bmp. Okay? So we'll be using that. And this is not going to work. Let's see. I did, and I had a 1680 by 1050 projector that I took advantage of. So I might have to do some side back and forth. But here I have an Android.bmp file, and then I have a white file. Both of them are 200 pixels by 200 pixels. And I'll dang it. I'm going to get creative with this.
So are you trying to generate key from these?
No. No, all I'm doing right now is just showing how image subtraction works.
Okay.
I'm not going to be able to scroll that. Let's see if I can do that. There we go. So when I subtract the green Android from the white blank screen, this is the result. And this isn't surprising. The opposite of white is black. You know, yeah, we got it, right? So that's the motivation. That's what I'm going to be doing. And I can see that I'm going to be pulling images to the side a lot. Okay, so let's look then at how, well, I did actually show how I did this. It's down here. Unfortunately, I can't scroll back. Anyway, I did the composite difference Android.bmp.
Alt space will grab the menu and you might pull the whole window up.
Control minus. Yeah, I did a control minus and made. I'm using S5 for the Solano just in case. That's all right. We'll see this code time. So let's look at some random files. Let's generate an image with random data and see what that happens when we subtract it. So first off, I'm going to generate a file, and I'm going to pull from the dev new random device. Before I begin, who can tell me the difference between dev urandom and dev random?
Urandom is less random than random. Random is from the, like the real random pool, and urandom makes use of a random number generator.
Okay? Close. Yeah, blocking is the key difference. Explain the blocking.
So random, when you draw from, it only gives you as it has a new number, right? Like if you create entropy by typing or whatever, but urandom always will give you a number.
So there's something called the entropy pool, and the entropy pool is, think of it like a bucket that has some numbers in it. Okay? These numbers are generated based on environmental input, keyboard presses, disk activity, network I/O, mouse movement. I've even seen Geiger counters that you can hook up to your computer and use radioactive decay. At any event, we want random environmental events to come into my computer, and those get stored into this bucket. Dev random will reach into that bucket as needed to generate random data. When the bucket's empty, though, dev random stops until more data goes into the bucket. Dev urandom will also pull from the bucket, but when the bucket is empty, it will generate a seed and continue to carry forth until there's more from the bucket to pick from. So the difference being dev random will stop working when the bucket's empty, dev urandom won't. Okay? So for our cases, dev urandom will be sufficient for generating quote-unquote pseudo-random and random data. So in any event, I'm going to generate a random 1.bmp, and I'm going to give it this size in bytes. The reason being is a 200 pixel by 200 pixel bitmap, if it's 24-bit, is exactly this size. And I'm going to take advantage of the bitmap header on that image and apply it to my binary file so I can open it up in an image viewer. So I generate a random 1 and a random 2. Then I apply that bitmap header from my blank.bmp. I apply it to random 1 and random 2, and it's 54 bytes in size. This tells the image viewer the dimensions of the file and other junk about it. Okay? This conf no trunk, this means don't truncate the file when you're done writing the data. In other words, I don't want a 54 byte file when I'm left, when it's done. I still want the original file, just modify those first 54 bytes and leave the rest alone. Okay, so I do that for random 1 and random 2, and I composite the difference. And this is really, really unfortunate, but this is what, let me, really quickly, if you'll bear with me, let me re-render this, see if I can get some better results. This is a big stink. Let's see. We'll try that. Let's go back. That was so better. There we go. That's doable. You might have to do this a few times to get through. But anyway, here's my random 1.bmp, here's my random 2, and when I compose the difference, this is what I got. And this shouldn't be surprising, should it? Random data doesn't have any structure, there's no pattern to it. And so if I generate 2 random events independently of each other and try and subtract them or compose a difference, I'm just going to get something else that does not have structure, that does not have pattern. Okay? So this isn't really too terribly difficult. Okay, so having this armed, our arsenal, our tools in our toolbox, this is how we're going to proceed with the presentation. We're going to use bitmap composition, and we're specifically going to use them towards file systems. Again, that's what we're going to be targeting, as I mentioned earlier. I'm going to start with the worst case implementation, work my way towards the best case implementation, and then we'll have a discussion at the end. It's important to understand that although these images help visualize what is actually going on, that's not rigorous. So don't get caught up on the placement of the file in the image. Don't get too terribly caught up on details in the image. Understand more or less what the image is trying to convey, if that makes sense. So first let's get some crypto terms out of the way, because we'll need them later. The first is electronic code block, or ECB. This is the simplest form of code blocking for encryption algorithms. And the way it works is I take let's say I take a plain text file. I chop this up into identically sized blocks all the way to the end. And we'll say the blocks are 128 bits in size. So if the file doesn't divide into 128 bits evenly, we'll pad the end of it until it does. Okay? Then we'll divide it up into blocks. The way ECB works is I have some sort of encryption algorithm. I'll draw it like a database. I send my block through the encryption algorithm, maybe this is AES, and out will come out my ciphertext block. Okay? And I do this for each plain text block individually, okay, all the way through to the end. There's an advantage to this, and that is I can parallelize the process. If I have a large file and I want the ECB mode encrypted, I can divide up, say, every 3 blocks, and give those 3 blocks to a process. So I can have 100 processes working on the file and screen through it. Big disadvantage, though, is identical plain text blocks get encrypted to identical ciphertext blocks. Okay? So things that have structure, like images, videos, music, that sort of thing, reveal their structure even after they've been encrypted. And we'll see an example of that in a second. Compare this to Cipherblock chaining or CBC mode. This is similar to ECB in that it takes my plain text, divides them up into blocks, But then we have what's called an initialization vector, or IV for short. This is a randomly generated number. Typically, we refer to it as a nonce, or a number used once. Okay? This initialization vector gets XORed with the plain text. That XORed result is what gets hashed. Okay, so this is my XORed result of plain text and my initialization vector. So this XORed product is what gets sent through the encryption algorithm, and it turns out to be a ciphertext. We store this to disk, but then we also take this and XOR it with the next plain text block. And then we'll take it and XOR it, and XOR it, and XOR it. And so you can see the chain that is created. The disadvantage to this is I cannot parallelize this process. It's very serial in nature. Each block is dependent on the previous, so I can't parallelize it. I'm stuck going through a single process. But a big win is identical plain text blocks are not encrypted to identical ciphertext blocks. Okay? So this works really well for integers and so forth, where their structures are completely different. So if we demonstrate this, in this case, I take my Android.bmp, I pipe it through OpenSSL, and I use AES ECB in 128-bit mode. When I'm done, I'll have this Android ECB.bmp. It'll just be a binary file. So again, I take my bitmap header, 54 bits in size, and I apply it to that binary so I can open it up in an image editor. Do the same thing with CBC. Let's see the result. So there's my Android. Here it is encrypted with ECB mode. Here it is encrypted with CBC. Now, by raise of hands, who can tell me this is the first time I've ever seen this? I mean, when I saw this, it blew me away. If you do a Google search for electronic codeblock, I know some of you have your laptops with this now, there's an example at Wikipedia that shows the Tux penguin, and they had a much larger image. My image is only 200 pixels by 200 pixels. They had a much bigger image. But they take the plain text Tux penguin, encrypted with ECB, encrypted with CBC, and you can see the results. You have much more detail in that Tux penguin because their image was so much larger. And that makes sense, right? If I have more pixels, more blocks, then detail is going to be preserved at 128 bits. Whereas if I have fewer, smaller, it's going to be harder to get out the detail. But nevertheless, it's there. We can clearly see it. And because this is CBC, this looks random. As I mentioned at the beginning, this is what we're targeting, right? We want encrypted data to appear as random data. And this is pretty close to what I started with earlier. So we think we're done, but we're not. We have not reached our goal. So let's look at file system bitmaps now. So we just did that with a single image. Let's do it with a file system and see how it works. So we're going to look at a plain text file system, UCB versus a CBC. And I'm going to do this two ways. When you decide to put an encrypted layer or an encrypted hard drive, you've probably read on a blog or in a forum or maybe at a Linux users group that you need to put a random layer of data down first. Very few that I've discovered understand why you need to do that, just that you need to do it. I'm going to demonstrate that here. So first we'll look at it without the random layer, then we'll look at it with, and we'll see if we can identify the difference. And again, our goal is to appear as a random bitmap. So I'm going to take this file, let's call it 0.bmp, and we want our file system, when we're done, to look like this. So we have our target, we have our source, let's see if we can reach it. So first, the plain text file system. Got some code here. This is all stuff you can run on your Unix-like operating system. So I'm going to pull from dev0, which just gives me a binary string of zeros forever. Okay? I'm going to implement a brand new, I'm going to, not implement, but imitate a brand new hard drive that has not seen any data into the disk yet. That's the point of the dev zero. I'm going to create this xt2-0.bmp file. That's going to be my file system, and I'm going to give it this size. This is the size of a 400 pixel by 400 pixel bitmap. I'm making it a little bit bigger, so when I copy my 0.bmp onto it, which is 200 by 200 pixels, we have enough breathing room that we can see what's going on. It doesn't feel so crammed. Okay? So now I'm going to take that file, and I'm going to turn it into a block device using the loopback system. Then I can put a file system on my file. I'm using xt2 because xt3, 4, XFS, and so forth want bigger file systems. Half a meg is not enough for some of the more modern file systems. xt2 doesn't complain, so we'll stick with xt2. But feel free to make a 500 meg file if you want and throw xt3 at it. I went with xt2. Okay, so then we'll mount it. We'll copy my 0.bmp over to the file system, unmount, remove the block device, and then lastly, we'll apply my bitmap header, and we'll apply it from a 400 by 400 pixel image. So the result comes up as 400 by 400 pixels. Does that make sense? Any questions on the process?
You have count still at 54.
Right. The bitmap header is only 54 bytes.
That makes sense. Thank you. Thank you.
Okay. So there's the plain text code. Let's look at the ECD code. Create a new file, xt2-ecd-0.bmp. Same thing. In this case, I'm going to use crypt setup, which is the encrypt encryption for file systems. And I'm going to say use the ECB cipher with AES on that file. I'm going to create a map disk called crypt disk that I'm going to be using, attach that to dev.0. So when I format, I'm going to be formatting dev mapper crypt disk. Okay? This is the cryptographic device that is inside of my encrypted partition, if you like. Mount it, copy it over, unmount, remove the crypt disk, remove the block device, apply the bitmap header. And we'll do the exact same thing with CDC. So I've created 3 file systems: plain text file system, ECD file system, CBC file system. And let me re-render this page. I really should have thought about the fact that I might be stuck with 1024 by 768. No, this isn't going to work very well. All right, well, how am I going to do this? I don't know. Let me,
Pass your laptop around.
I was going to say, let me put this on my screen. I don't know how well you can see that. Not very well. Let me email me for slides. If I plug in, it should write on the screen.
You have Python running, and are you on the wireless? You can always just fire up a simple web server besides.
I'm not on the wireless. All right, let's try this. How about that? Better?
Not from back here.
Apologize.
You just use it, just right click.
Yeah, that's a good idea. That's true. I can actually print the PDF right here.
You got all the tech support you need.
Yeah, that's true. I do know.
More than
Some of the raw words we have in this room.
I'm generating a PDF.
Sweet.
I'm sorry, guys. So Control P to print. File. PDF. Printing. I always say when things go wrong, because the room gets really hot. Anyone else notice that?
I think it's
It was just me.
It's just you.
Oh, okay. Now this will have my notes as well. So I'll be doing some scrolling. How can I kill the thumbnails? Open. If anyone wants to do a song and dance while I'm ready.
You.
Progress. Alright. There we go. Looks like the page is breaking it. But this is what we wanted to see. Alright. Here is my plaintext file system. Here is my ECB file system. And here's my CBC file system with the page break in the middle.
Okay.
So we can kind of make out what's going on, right? We can see on the ECB, just like we'd be expected, we can see the patterns of my zero. So the image structure is being held in place, where with the CBC, we get what appears to be random data. Now, who can tell me what this black is? Zeros. So what does this mean?
No data.
We know it's encrypted. Even the random data, we know there's something there.
Right. As an attacker, where am I going to put my effort? I don't need to go over the whole disk because you didn't put down the random data beforehand. I can clearly see where the encrypted data lies. I'll ignore everything else. Right? Okay. So let's redo this. This time though, let's do it with dev-urandom. So I'm going to use the dev-urandom device again, generate my file, and then go through and create the plaintext file just like I did before in the plaintext file system. But this time, because I used dev-urandom, my disk has now been populated with random data. Okay? We'll go ahead and set up the ECB file system. We'll set up the CBC file system. And as a result, this is what we get.
Yeah.
Now it's clear why I need to put down a random data on the disk beforehand, isn't it? Because if I'm using CBC, I can't identify where the random data begins or ends, and where my files end or begin. Right? So now the attacker has to cover the whole stupid project. Okay. So we went from a worst case scenario, in this case with dev0, to a much better case scenario with the random. Now, because we have a CBC file system, I'd say we could toss our hands up in the air, success, we're finished, right? Unfortunately not. And this is where it gets really, really fun. So, seems about the text size now is a little small. I wonder if I could leave if we go back and forth. Just do that. So at least I can make the text much bigger. Okay. So we haven't met our goal. So let's introduce what's called the snapshot attack. To motivate the snapshot attack, for those who don't know, I work at Encryption. greatest place on earth. Absolutely. I really do. Like, I'm not lying. It's a blast to work there. I have a workstation where I have two 250 gig hard drives, and I've put them in a stripe. So, should one of those die, I run the risk of completely losing my data. So I'm backing my data up every 6 hours to an external 500 gig hard drive, and that sits on top of my workstation. That hard drive is also encrypted. Now we have a cleaning lady that comes through like 11 p.m. every night and cleans the office. Let's pretend for a second the cleaning lady is really Tom Cruise, Mission Impossible. Right? Rips the mask off. She has access to my workstation. She's got physical access. She's in the office. So she's going to take my hard drive. She discovers it's encrypted. Rats. Well, I've got access to petabytes of storage and supercomputer clusters. I'm going to image this hard drive. So she starts the imaging process, cleans the office, and then by the time she's done cleaning, the image is finished. She's got her image on her computer. She does this night after night after night, continuing to image my 500 gig hard drive. Meanwhile, I don't know what's going on. Okay? She now has images of my hard drive. The snapshot attack is exactly what we've been doing with these bitmaps. She's going to compose a difference between two successive snapshots and get a result, and then move to the next successive two, get a result, next successive two. Now she's got composite results. She can snapshot those against each other, continue in a like manner, revealing data the entire time. And if you don't believe me this is possible, you've got half hour. So, unfortunately, as cool as CBC is, it still can leave information about what it's containing. And we're going to demonstrate this 3 ways. The first is single key, simple initialization vector mode. It's a mouthful. Basically, all this is password protection, right? If you encrypt your thumb drive and it says, provide me your password, that's what simple key is. The password is the motivator for encrypting and decrypting the data. Multi-key mode is where not only do I have a password or passphrase, but I also have a physical key, whether it be a smart card, maybe a GPT key that already exists somewhere else. But it's like it's almost like two-factor authentication. There's something I know and something I have. Okay? That's the multi-key mode. This 128-bit AES CBC SSID phone shop 25th should be very familiar to you. This is the LUKS default. If you format a drive with the LUKS container and don't modify any of the options, this is the current default. Okay? So let's go ahead and look at those. So first, the simple IP layer. In this case, I'm just going to demonstrate with an image. We'll get to the file system later because I want to really show how well this leaks. I'm going to use AES pipe, use my 0.bmp, output the result as AES 0.bmp. So I have an encrypted 0 file. Do the same thing with a blank. Okay? I'm going to apply the bitmap header. This is what I'm doing on these 2 lines to both files, to both the AES 0.bmp and the blank.bmp. They will compose the difference. And as a result, let's go back to my PDF. This is what we see. So here's my 0.bmp file encrypted, CBC. Here's that blank that I did earlier with the Android, which is the 200 pixel by 200 pixel white file. And when I do the composition, what do you see? I see the 0. I don't know about you. I mean, maybe it's hard with the projector, but there is definitely, and even the dot in the center, my 0. And in fact, I can bring them side by side, and you can see maybe a little more clearly. Here's my 0.bmp, here's the difference, the result, and here's what I'm trying to achieve. We're a long way from it, okay? This is single key AES, okay? All right.
But you have to know the key.
No. The key is completely secret. I generated those 2 bitmaps, and then just using the composite function, I just subtracted one from the other, and that's what came out. I don't know the key, didn't need the key. All I needed was binary data. All right. So now let's do it with multi-key mode, multi-key version 3 mode. The first command, don't try and really make a lot of sense of it. Ultimately, all I'm after is an open PGP randomly generated key. So that's what I want after. Now I'm going to use that key with AES pipe, just like I did before, and I can turn AES pipe into multi-key mode by passing the -k switch. So I give it the key I generated, do the same thing, read 0.bmp, output the encrypted result, do blank.bmp, output the encrypted result. These two lines apply the bitmap headers, so I can open them up in my image editor, then compose the difference. And we get this as a result. Here's my multi-key 0.bmp, my multi-key white file, and then the result. That looks a lot better. Actually, I'm really impressed with those results. But who wants to make a guess
That's the zeros.
at where the beginning and ending of those lines are? Well, if we look closer, it's exactly where the zero is. Right? At the top and bottom of the zero file line. So although we've obstructed what the data is that is contained, it is still limited to structure of the file itself. Right? So this would seem like a much better practice. And I'll talk about this at the end, but we're going to continue forward with LUX. So let's do that. So now let's do LUX. Again, I'm going to generate, in this case, I'm going to do a full file system, just because LUX format expects that. So I already know that I need to fill my file system on my block device with random data. So I do that, create a file with random data, and I'm going to make it a meg in size, a little bit bigger. I'll attach it to devloop0, so it's a block device, and then I'll use this LUX format. This is calling the LUX extensions in decrypt. The -S128 to align payload equals 8. Previous LUX versions didn't have a minimum file system or minimum block device requirement. Current versions do. This removes that requirement. If I take that out, I can't format the 1 megabyte block device. It has to be a lot bigger. So that's all that is doing for me. So I'm encrypting devloop0, and I open it up, and I create again a block device that's going to be mapped to my devloop0, and this will be devmapper AES script, as I'm calling it. Format it, mount it, copy the file over, unmount it, close the device, remove the block device. Now, this is day 1. I'm kind of going after day 1, day 2 mode here. Here's day 2. I'm going to copy now my new file system that I just saved to another, and then go through the same process, but in this case, I'm going to modify my file, and I'm going to put the blank.bmp in its place. Why not just generate and format a new block device? The reason is, a new initialization vector will be generated, and the resulting crypto on the device will be entirely different. In practice, we don't do that. I mean, I'm running a LUX formatted drive. Every day, I don't take my data off, reformat the hard drive, put it back on, right? I just decrypt it, edit my files, and work. So that everything on the file system stays the same, except for the files I'm modifying. That's what I'm trying to go after here, right? So I'm modifying my file. Unmount it, apply the bitmap headers, compose the difference. And the result we get is this. So I have my 0.bmp. I copied it over and put the blank.bmp in its place, compose the difference, and this is what I got. In other words, the day 1, day 2, I made some modifications to files. And when the maid lady does a snapshot between the differences, this is what she gets. Those are kind of 0 instruction, aren't they? So it's revealing actually quite a bit of data. This is unfortunate. I would expect LUX to be better. Okay. Any questions so far? I feel like I'm going fast because I lost time trying to generate the PDF and deal with the 1990. Okay, then let's go forward. So let's do the best practice then. The best practice seems to be multi-key mode. We saw how well that hid the data, even though it was still restricted to physical geometry of the data it contained. Although with that, it did fairly well. Unfortunately, Lux does not support multi-key mode, and Lux is the most common encrypted containing system for Linux. There's also TrueCrypt, which seems to have a good following. It's open source as well. But Lux seems to be the king of the hill on our side of the fence. So we'll stick with Lux. We don't get multi-key mode. That sucks. So we're going to have to figure out how to do a best practice with what we've got. So I'm going to make some recommendations. How about after I've got the file system formatted and mounted and I'm working like I am now, how about we fill any remaining free space with random data? And we do that every day. Move the file, refill it. Move the file, refill it. And if you think about that, that's really kind of trivial. I could, at 6 o'clock, kickstart the process and go home. I don't care if it takes 5 hours to fill 500 gigs, because by the time I get back and I'm done, I can move the file and work. And then when I'm going to leave, just kickstart the process again, go home. So it might be expensive, but it's not impacting my productivity. Okay? So it's something doable. Another thing we could do is intentionally fragment the file system. We'll talk about the motivations on that in a second. Right? So on day 2, I'm going to make the modifications. I probably should have reversed these 2 steps. But remove the waste file, make my modifications on, on doing my work, whatever it may be. Then when I'm done, recreate the waste file. Unmount, apply the bitmap header, da 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 da. Let's see where that gets us. And that is the result. So here's my file system that I put the 0 on and then filled. Here's where I made my modifications that I worked throughout the day, and then recreated another waste file. And when I did the snapshot, here was the result. So this looks a lot better than what I had on the previous Lux, right? I still have my file showing up, so I've got to do something about that. But the rest of the file system looks random. It's not open. And if I continue to do this, like we saw, random data subtract random data is still random data. As much as the evil maid is still snapshotting, she's still going to get this, which is good. So we're out. And for comparison, again, here's our target. Here's what we got. What can we do? We're almost there. What can we do to do this? So let's talk about fragmenting the file system. Solid state devices like SSDs, USB thumb drives, SD cards, your phone, any solid state device isn't restricted to physical moving parts. Right? There isn't an actuator arm jumping all around the disk trying to access data. We just have matrices and chips, and we just go. So fragmentation is really a non-issue on solid state media. So, I mean, performance-wise, on a platter, you're screwed. But for solid state stuff, let's see what encryption gains we can get out of intentionally fragmented processing. So, let's set that up. Again, we go through the rigmarole, random. Actually, this is a plain text file system. I want to see what it looks like, just to make sure that my motivations are in check. Okay? So I'm going to create a 1 meg file, attach it to devloop, and then do my format. The stashen 1024, I'm telling the file system I want exactly 1024 inodes. Who in here can tell me what an inode is? Why?
It's the basic block for files, but it's just block file containing. Exactly.
So if I have a file system with 1,024 inodes, what does that mean?
You can have a max of 1,024 files.
Right. So the inode is like metadata that describes the file. And if I create a new file, I have to occupy an inode to store that metadata. What happens when I fill up those 1024?
Can't be any more files.
Even if I've got like 300 gigs of unused hard drive space?
Yep.
Exactly. So you could have a full file system, and all you've done is exhausted your inodes, but you've still got plenty of physical disk space to go. With a 1 meg file, XT2 only gives me like 150 inodes. It doesn't give me very many. So if I'm going to fragment the disk and really see the benefits of what I'm going after, I need to give a lot more. So that's what I'm doing, giving you 1,024 inodes instead of the few that you give me. Another thing that sucks about that is with XT, once it assigns those, they're static. There's no change. If you want to change them, you need to reformat your file system. Sucks, but that's what it is. Okay, so I mount it, and this for loop is creating 1,024 files. They're all 1 kilobyte in size, and I continue to populate 1.waste, 2.waste, 3.waste, all the way through to 1024.waste. Okay? Then, after it's done creating these 1,024 files that are all kilobyte in size, I remove every file that ends with a 7, or every 3-digit file that has a 7 in the middle. Okay? Or I guess that could also be a 1 or 2-digit file as well. At any event, I'm putting holes in the file system. Okay? Now I copy my 0.bmp over. So that 0.bmp is going to fill those holes. It'll be intentionally fragmented on the file system. Go ahead and set it up, and here's the result. Which is 0.bmp. Here it is on the file system. It's a lot different than what we did before at the very beginning of the lecture. Okay, so now, what would this look like on an encrypted file system? Let's find out. So now we're going to set up an encrypted file system. And again, I'm going to create these 1,024 files. In this case, I've changed the algorithm a little bit. I'm removing every file that ends with 4 or 7. Copy the 0.bmp over. And then I already learned that filling the file system with random data was a good idea. So I'm going to apply that here. So let's do both fragmentation and filling at the same time. So I fragment, copy, any remaining fragmented space I have, let's fill it up. Unmount, remove the block device. Day 2, do the same thing. Now, on day 2, I'm not going to remove my .waste files. I figure, knowing that the snapshot attack removes similar data from image to image, why don't I rewrite these fragmented files with random data? So they're different the next go around. Okay? Make my modifications. Again, fill up any remaining space. Unmount, apply the bitmap headers, yada, 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 and the result ends up as that. So, let's put both. So here is my fragmented, and the 0 is copied. Here is the extra work I did in that previous slide, and here's the result. At this point, I can't get it any better. And this is pretty damn good. The few striations and lines in the file system are going to be part file system metadata and maybe part files, but for the most part, I've almost achieved what I wanted to achieve, right? And with the file system metadata, there's really not a lot I can do about that. I could maybe change, do the file system name or, do some minor file system tuning, but overall, it's not going to affect that structure. And with our goal and what we wanted, we started with 0.bmp, we ended up with this. This is what we want. I think we do. Any questions on that? Do I actually do that? The $1 million question.
I thought the question I answered was I could use it
That's exactly what I was going to say. I have not intentionally fragmented my backup hard drive. No, I didn't think about that beforehand. Second, and this is some considerations that I put on this screen, is I'm actually using ZFS for the backup hard drive with Debian. There's a ZFS Linux module coming out of the Lawrence Livermore laboratory, and it's awesome. Like, they've got Perl version 28, which I think is the latest version that you can get legally, because I paid for Perl. Not releasing the source code, I don't think the remaining Perl versions are available to the community. That's weird, I'm wrong. So I think 28 is the latest we can get, which is unfortunate because 30 is when they implemented native encryption in ZFS. So I'm using the Lux container and I'm putting ZFS inside Lux container. But in any event, to answer your question, I didn't think about fragmenting the file system when I started. But I do have a cron job that kicks off at 8 p.m. and does fill up the hard drive. And then at 6 a.m. it's finished as I can do it. So when I get into work, I've got
So an attacker could still come in and derive the key out of the state plan because the system is still
yes, the system is still on.
Which would be a lot easier with any of these.
Yeah, for those who are familiar, there is also what's called the cold boot attack and the evil maid attack, which is a snapshot attack. The cold boot attack is the idea that when volatile RAM loses power, it doesn't zero out immediately. It kind of degrades towards zero slowly. Okay? So if I can get the RAM out of the system down in a cold boot fashion, I don't want to do a proper shutdown because then it will erase the contents of where the key's provided. So I rip the power out. Okay, the system's down. Yeah, I can see a few faces going.
You don't even have to rip it out. You just flip it over, spray your Freon and the thing, and then pull the memory right out.
Pulling memory out on the power system might cause some electric concerns with the RAM. I feel safer cutting the power, freezing it maybe, then cutting the power, then pulling it out. But that's where the cold boot attack comes from, is if you do freeze it with compressed air, you can get, instead of 5 minutes before it zeroes out, maybe even a half hour. Keep freezing it, you can sustain the contents of RAM much longer. So I could put them in another computer that reads the contents, get the key out, and now I've got access to the process. The evil maid attack is where I would modify your bootloader and put a keylogger into the bootloader. So when you boot up, you're none the wiser. You type in your passphrase willy-nilly, and it stores that to disk, and as soon as you get network access, maybe it sends it over the wire to the remote server. So the evil maid can come back into your hotel room the second night, type your passphrase, and get access to your
Boot CDs. Use that instead.
Yes.
Don't use it. Don't put the bootloader on the other device. Separate the device from functional.
Oh, there you go. Yeah. Yes, there are ways to definitely. So coming back to the snapshot attack, here's some things that I have not considered in this presentation. So I'm going to bring them to you, and if you're interested, you can study them on your own. Things like RAID. What if I implement a RAID 0 strike across 10 devices? My file is chopped up. It's striked across the 10 devices. And if I image a single device, what sort of patterns could I reveal? What sort of information could I leak out of the file system that can strike RAID? Or what if it was parity-based? Now that I've got parity, like a distributed parity RAID 5 and RAID 6, how would that throw a monkey's wrench into the snapshot attack? What about logical volume management? With logical volume management, I can decide where I want my physical extents to go, which are the blocks that contain my data. I can target them on a specific drive or spread them across multiple. How will that throw a wrench into the snapshot attack? XT, XFS, JFS, Riser, they're all linked to file systems that go after each model. More modern file systems are copy and write, like ZFS or ButterFS. Copy and write uses a much different model, with modifying data. So how would that look? Again, or if I take LVM snapshots, ZFS snapshots. If I introduce compression, compression's interesting because it introduces entropy to the system. So if I compress my file and then store it on the drive, can I get anything out of it? I don't know. And deduplication is either file-based or block-based. Either I remove all duplicate files on the file system and just provide pointers, or I remove duplicate blocks. So again, I can save kind of a form of compression, or I can save disk space. But if I'm using deduplication on the block level, let's say I have a file that maybe a few blocks are duplicated somewhere else. Those blocks aren't going to get written, but instead of pointing to them, I'm pointing to them. So am I going to see like a sparse file? What am I going to see? I don't know. So these are, I did actually want to put ZFS and ButterFS in the presentation. The ButterFS requires a minimum 250 megabyte file system, and I couldn't figure out the minimum size for ZFS, but it wasn't even meg. So, but anyway, just some thoughts. So, in conclusion then, we learned the difference between ECB and CBC mode, how ACB is fast, but we're kind of screwed up with structure being maintained in the encrypted system. Where CBC is slow, but not necessarily slow, it's slower, and we removed that structure. We learned that we should put random data down on the file system first, and that the snapshot attack is a fairly effective attack against drive images. And then I mentioned a daily routine where maybe we start, if you have a USB thumb drive, either solid state or the drive that's platted but you don't care about performance, like my backup drive. You can intentionally fragment it, overwrite the fragmented bits with data, remove your waste file, do your work, put the waste file back in the play, and go home, wash, rinse, and repeat. Let this do its work while you're at home. So, some thoughts. Lastly, I need to owe a great deal of acknowledgement and thanks to Dr. Basil at UIC. Initially, when I was investigating this, I discovered that Tux Penguin on Wikipedia, and it just blew my mind. Like, it opened up my world to encryption, and I wanted to know how they did that. And after I started developing things, I stumbled upon his PDF, and I thought, wow, this is an effective way of doing drive analysis. And so a lot of my presentation is motivations from his PDF, so check that out.
So is that in Canada, in France?
I'm not sure, actually.